The first section in Chapter 5 is titled Identifying Linear Functions. We start by defining what a linear function is, and it's simply a function whose graph forms a straight line. So you can see here we have an example of a linear function because the graph forms a straight line. So we need to identify whether each graph represents a function, and if so, is the function linear? So as we look at number 1 and we look at the graph, first of all, is it a function? Remember, graphically, we tell if a graph is a function based on if it passes the vertical line test. And you can see here that this line does pass the vertical line test. If we draw vertical lines through the graph, we only touch the graph one time. So yes, it's a function. Then the question is it linear? Yes, it's linear. So yes, function. And yes, linear. So does it pass the vertical line test? Yes, it's a function. And then is it a straight line? So let's look at number 2. First of all, is it a function? And then is it linear? So as we draw vertical lines through the graph, we can see that each vertical line is only touching the graph one time. So it is a function. But hopefully you can see that it is not linear. It does not form a straight line. Number 3, it does appear we have a straight line, but remember a vertical line, if I draw my vertical line using the vertical line test, and let me change colors here so it's easier to see. If I draw a vertical line through the function, notice my vertical line touches the function everywhere. So this is not a function. And obviously, if it's not a function, then it's also not a linear function. Now we have an example. We have a horizontal line. So is this a function? You can see yes, a horizontal line is a function. And it is linear because it forms a straight line. Number 5, we have a sideways parabola. That's what a U-shaped curve is. And as we check if it passes the vertical line test, you can see the vertical lines I'm drawing are intersecting the graph in 2 different places, so it's not a function. And again, obviously, if it's not a function, then it's not a linear function either. So now let's talk about identifying linear functions if we don't have a graph and maybe we just have a relation or a set of ordered pairs. So you can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in x will correspond to a constant change in y. And that has to deal with slope, which we'll talk about in a section a little later. But as we look at this chart, you can see that every x value is increasing by 1, and every y value is increasing by -3. So this is a function because the constant change in x is corresponding to a constant change in y. So let's look at some more examples. Tell whether each set of ordered pairs satisfies a linear function. So if you want, you can list them in a table. Sometimes it's a little bit easier this way. That way your eyes kind of don't play tricks on you. But let's list the x values, 0, 4, 8, 12, and 16. And the y values are -3, 0, 3, 6, and 9. And you can see we are adding 4 to all the x values. And the y values, we are adding 3. So it is a linear function. And it does say to explain. So your explanation should be something to the effect of constant change in x corresponding to a constant change in y. Here's another example. Again, I'm going to list them in a table. So we have -4, -2, 0, 2, and 4. And those are increasing by 2. And for the y's, we have 13, 1, -3, 1, and 13. So here we have increase by -12, increase by -4, increase by 4, and increase by 12. So not a linear function. And why? Because the constant change in x does not correspond to a constant change in y. These numbers are not the same. It could be a function, but it is not a linear function. You'd like to pause the video here and try this one on your own. I'm going to try to do this one without listing it in a table. So I'm looking at 3 and 5, 5 and 7, 7 and 9, 9 and 11. It looks like it's +2 all the way. 5 and 4, 4 and 3, 3 and 2, 2 and 1. And you can see we're increasing by a -1. So yes, it's a linear function. And again, what's the reason? Well, the constant change in x is corresponding to a constant change in y. And also recognize that what it's changing by doesn't have to be the same, it just needs to be constant. So now let's look at identifying linear functions without a graph or even a table of values. So now we can determine whether a function is linear by looking at its equation. And a function is linear if it's described by a linear equation. And a linear equation is any equation that can be written in standard form. And standard form of a linear equation looks like this. And I want you to write this part down. ax plus by equals c, where a, b, and c are real numbers, and a and b cannot both be 0. So it's kind of a fancy equation, and we'll work with linear equations or standard forms a little bit later in this chapter. But basically what this means is x and y must both have exponents of 1. So we can't have x squared, y cubed, anything like that. Also, x and y cannot be multiplied together, so no x times y. And x and y cannot appear in denominators, exponents, or under radical signs. So now let's look at some examples of linear and nonlinear equations. On the left, we have a lot of examples of linear equations. And what they've done is proven that they're linear by rewriting them in standard form. And we actually don't have to do this just yet. We can actually tell if equations are linear based on those 3 criteria here on the last slide. So this is what you really want to make sure you're paying attention to. And on the right-hand side, you can see why they're not linear. We have x and y multiplied together. We have x to the 3rd power, and we have y in a denominator. Those are all things that will rule out whether or not an equation is linear or not. So it says, tell whether each function is linear, and if so, graph the function. So on number 9, we have x, y equals 4. And hopefully you're saying it's not linear. And why is it not linear? Because x and y are multiplied together. But on number 10, we have y equals 5x minus 9. So we don't have x and y multiplied together. We don't have exponents on x or y other than 1. And we don't have them in denominators. We don't have x and y in exponents. And we don't have x and y in radical signs. So this is a linear function, number 10. So let's make a table of values and graph it real quick. Anytime you're asked to graph a function, if you can't remember what to do, you can always make a table of values. So remember, if we don't have a domain, we usually do -2, -1, 0, 1, and 2. If I plug in -2, I get -10 minus 9, that's -19. If I plug in a -1 here, I get -5 minus 9. It's -14. 0 is -9. 1, 5 minus 9 is -4. 2 times 5 is 10. 10 minus 9 is 1. And remember, the other thing you can do is you can check for the constant change. Okay, these are all increasing by 1. This is just another way to verify that it's a linear function. And what's happening with the y's? Well, it looks like they are increasing by 5. So let's just make a graph real quick. The first ordered pair is -2, -19. I'm going to put that way down here. Let's go 5, 10, 15, 20. I'm going to move that one up a little bit. These are going by 5s. We also have -1, -14. We have 0, -9. We have 1, -4. And we have 2, +1. So you can see if we connect the dots, because now with all of our linear functions, they are going to be lines, and the domain and range will be all reals, so for the most part. So yes, we are going to connect the dots, and we are going to draw arrows on both ends because these are lines, so they extend in both directions. Let's take a look at a couple more examples. Here we have y equals 12. So we're trying to determine if this function is linear. Remember the rules. X and y can't be multiplied together. They're not. X and y cannot have exponents other than 1. They don't. Y has an exponent of 1. We have no variable in the denominator, no variable in an exponent, and no variable under a radical. Now what we might point out here is that we actually don't have an x. But if I go back to the slide that had the explanation of linear functions, it says that a and b cannot both be 0. Notice a is in front of the x and b is in front of the y. So if we have an equation where we actually don't have one of the variables listed, it can still be linear. It can still be a function be linear, because what happens here, if I write this in standard form, remember standard form is ax plus by equals c, the a is a 0. We have 0 x's, we have 1 y, and it equals 12. So this is written in standard form. Now what's nice about this equation is it's really easy to graph. When we have a graph and it says that y equals 12, it means all the y values in every ordered pair are 12. So if I go 5, 10, 15, so there's 12. This is what the line y equals 12 looks like. It's a vertical line that goes through 12, because any ordered pair I pick, -2 would be 12. 10, 12. Those are all ordered pairs. 0, 12. So that one's pretty easy to graph. On number 12, is this one linear? And you hopefully are saying not linear or no. And we see the exponent, the variable up in the exponent. So we don't need to graph it because it's not linear. In class, we'll work on worksheet 5.1.